In this last section, we're going to look at multivariable integration. And this is going to be very similar to what we did in terms of the applications of integration that we did in Chapter 7. We are not going to go back and do all of the basic properties and all of that for integration, but you will see that they fall in to some of the problems that we do here. Here, what we're mostly going to be looking at are our geometric representations of figures. So first, I need you to go back and to recall, when we first started talking about area, we talked about a function f of x, and we looked at the area under the curve over an interval. And then we expanded this to talk about the area between two functions. And so here, if I have an f of x and a g of x, the integral from a to b of f of x minus g of x dx gives us the area between the two functions on the interval ab. Multiple integrals are another way to find these areas, but more importantly, we can expand this to find volumes as well. And so there's a couple of different things to keep in mind. I'm writing up a bunch of formulas here, and you don't have to remember all of these, but they all have some similarities in them, and you'll see them more when we start looking at the pictures. So the first is for area. I can think of it in the one variable sense as the difference between two curves, or in a two variable sense, I can think of the area as being given some function f of xy, whatever that function is, it's the region defined by that function, and if I take the multiple integral over that region, that gives me the area. Okay. Again, here it doesn't make too much sense, but we'll see when we get the pictures. There are two different representations for this two variable picture, and that depends on whether I want to integrate y first and then x, or whether I'm integrating x first and then y. And so here you can see, in this case, x is between a and b, y is between c and d, but if I switch those, my limits are going to change. I can't just change the a and b and c and d. They do actually become new limits for the x's and y's. Likewise, in a two-variable system, I can also find the volume of a function. And notice here the main difference between the volume and the area in a two-variable system is that the area doesn't have a function in there. You can almost think of that function as just being one. We are truly defining it over the region. But now if I add the function into the region, I can think there's this region and I'm looking at some function over it, and that's what's giving me my third dimension for my volume. And so here again, same thing. There's two different ways I can write it. Again, where my limits are going to change slightly depending on which way I integrate first. So then I can expand this to volume. So if I add another variable to my system, then I can think of a three-variable function. And again, if I just look at the integration over the solid, so it's not just a region anymore, but some three-dimensional object, if I look at that region for my x, y, and z's, integrating over that surface or solid is going to give me the volume of that solid. Okay, and again, you can expand this for more integrals, but this is probably the extent that we're going to do. So we're not going to look at four variable functions where we're integrating over three of these to get a hypercube. No, we'll stay with the 2 and 3 variable. Okay, so to kind of explain this a little better, let's look at some generic f and g. So I've got two functions. I'm going to call this red one my f and this blue one my g. And these are both functions of x, and I'm going to have some interval from a to b. Okay? So basically I'm looking at this region in here. Okay? Now, in the one variable sense, we would actually call f and g two separate functions, and we'd integrate. And we know how to do this. We would say this is going to be the integral from a to b of our f of x minus our g of x dx. Okay, so it would be the upper minus the lower curve, and we'd integrate over that region. Okay, now in two variables, what this is saying is instead of treating these as two separate functions, I can come up with a region that I'm going to integrate over. So in two variables, my area, so looking at this exact same picture, and notice here, I haven't changed my function. So even though I said I'm looking at an x and a y, I really am thinking x and y, it's just I don't have a specific function for those two variables. And so here I'm truly integrating over the region, where in this case, if I'm looking at this by my setup as we said over there, I could have more than one setup, so it could be dx dy, but for this representation, just to show you the difference, I'm going to leave it as dy dx. So here, in the two variable sense, what this is saying is I'm going to start by looking at y's and figuring out where my y values start and stop. And so in this case, I can see that my y values start, meaning if I take any vertical line and go upwards, my y values are going to start at g of x, and they're going to end up at f of x. And then I'm going to integrate with respect to x, which we can see the x values, so if I take some horizontal line, where they're going to start and where they're going to stop are just going to be from a to b. And so one of the things you'll notice between these two functions is if I look at this, when I integrate with respect to y, I'm going to get an antiderivative here, and I'm going to evaluate at the upper minus the lower, which is essentially going to give me this integral here, which is my one variable integral formula. So these truly are the same thing. And again, notice I don't have a function of two variables here, even though I'm thinking of it as a multivariable integral. Okay? So in order to find area and volume using multiple integrals, the first thing we've got to be able to do is evaluate multiple integrals. There are some other steps that we're going to have to talk about, but first let's look at evaluating some multiple integrals. The steps are really straightforward. Basically, all we're going to do is, if I'm looking at a two variable system, meaning an x and a y, so two integrals, I'm going to start with the innermost integration, and I'm going to integrate with that innermost variable first. What that means when I say with respect to that variable is everything else, just like when we did partial derivatives, is treated like a constant. And so when I integrate, I'm only going to integrate those things that have that particular variable in it. Once I integrate and get my antiderivative in terms of that variable, I'm going to evaluate based on the limits for that variable. The next thing I'm going to do is then integrate the remaining integral. So there's going to be one variable left in my problem, and I'm going to integrate with respect to that variable. This is the step where it goes back to just a single integration type problem that we've dealt with back in Chapter 6 and Chapter 7. And then, again, I'm just going to evaluate upper minus lower. Okay? So let's look at a couple of these types of examples. So this first one, I've got a nice function, x, y. I want to integrate this with respect to y and then x, where y is going from 3 to 4 and x is going from 0 to 2. This is what I consider one of the basic ones, because if I look at the limits in both of the variables, they're constant. Okay? There's no variables in my limit here. And some of your functions you will actually have variable limits that you're going to deal with. And so we'll look at that in a minute. But in this case, it's nice because they're constant. So what it says to do is I'm going to start with this innermost integral first. Okay? So the 0 to 2 and the dx, I'm not really going to worry about right now. I'm going to just work on that inside. So I'm going to take the antiderivative of xy. Again, because I'm doing it with respect to y, the x is treated like a constant. So in this case, my antiderivative is going to be 1/2 x times y squared. So think 1/2 y squared is my antiderivative. And I'm going to evaluate this from 3 to 4. And I'm evaluating the y's, not the x's. So the x's are just going to stay there. Okay? I'm going to scooch this over just a little bit so it doesn't look like I left too much of a big space in there. Okay? Again, the 0 to 2 is just going to stay there. And now I'm going to evaluate that middle piece from y going from 3 to 4. So at my upper limit, I'm going to get a 16 over 2, or an 8x, minus, at my lower limit, 9 over 2, x. And again, my remaining variable there is a dx. Okay? Again, simplify it down, so that's part of my evaluation. So now I'm looking at the integral from 0 to 2. 16 minus 9 is 7 halves x dx. Okay. Now again, at this point, I'm back to just a single integral. There's only one variable in here, and now this is basically what we did back in chapter 6 and 7. I just want to integrate this with respect to x. So here, now doing this integral, I can see my antiderivative is going to be 7/4 x squared, and I want my x's to go from 0 to 2. Okay? So here, I'm going to get a 7 over 4 times 4 minus 7 over 4 times 0. And here we can see there's going to be my solution. Okay? Let's look at another one. Now in this case, this one's a little different because now when I look at it, my limits in both cases are not constant. Okay? One thing to keep in mind here is no matter what your integrals look like, if I have non-constant limits, they are always going to be on the innermost integral. You are never going to have a multiple integral where the outside limits have variables in it. And that's again because if I'm trying to find an area or a volume, I should end up with a number. And so if I look at those last integration limits, if they're variable, then I'm going to end up with a function out here, and that's not what we want. Those outside limits should always be constant. Now, even though these limits are variable, I'm still going to treat this the same way. So again, looking at this, I'm going to start by looking at the x cubed minus xy, and I'm going to integrate that with respect to y first. Okay? So here, my integral from 0 to 1, my antiderivative of my x cubed minus xy, again, this is with respect to y, so x's are treated like a constant. So x cubed times y would be my antiderivative of x cubed, and then here, minus a 1/2 xy squared is my antiderivative of xy. So again, I'm just treating x like some coefficient, the y's get attached onto that. Again, I'm going to evaluate these from y equaling x cubed to x squared. And then I'm going to integrate that with respect to x. Okay? So in this step, again, I'm going to go ahead and carry down my limits, so the 0 to 1. I'm going to go ahead and evaluate. So at my upper limit, it looks like x cubed times an x squared, or x to the 5th, minus, plugging in x squared there, I'm going to get x squared squared, which is x to the 4th. So we'll get a 1/2 x to the 5th. Minus, at the lower limit, plugging in the x cubed, looks like x to the 6th, minus x to 1/2 x to the 7th. Okay. Again, before I go on, I need to simplify. So simplifying this, 0 to 1, we can see I'm going to get a 1/2 x to the 5th minus x to the 6th plus 1/2 x to the 7th. That's going to be integrated with respect to x. Okay. Again, just like in the last example, at this point I'm now back to an integral that we've done before. It's one variable, so I just find my antiderivative, which in this case is a 1/12 x to the 6th minus 1/7 x to the 7th plus 1/16 x to the 8th, and I'm going to evaluate that from 0 to 1. At my upper limit, plugging in the 1, I get 1/12 minus 1/7 plus 1/16. At my lower limit, notice when I plug in the zeros, I'm just going to get 0. So simplifying here, I'm going to need to get a common denominator. So here I'm going to need to multiply by 4 times 7, or 28. Here I'm going to need to multiply by a 16 and 3, looks like a 48. And here I'm going to need to multiply by 3 times 7, which is 21, all over my common denominator. So simplifying, it looks like a 49 minus a 48, so 1 over 326. Okay. So there would be my solution for that multiple integral. So the first... So now that we know how to integrate or evaluate integrals or multiple integrals, the next step in being able to solve area and volume problems using multiple integrals is to be able to figure out how to define your region. And it's going to be different for every set of functions that I'm looking at depending on how my region is described. Okay? So the main kind of algorithm for setting up your region is as follows. The first thing I'm always going to want to do is to figure out which order of integration I want to do. So if I'm looking at a two-variable function, I have the integration dy dx, or I have the integration dx dy. And it is going to depend on a couple of things. One, it's going to depend on what your region looks like, but it's also going to depend on my function. Some functions I may not be able to integrate with respect to one of the variables very easily. In some cases, especially if I'm looking at an area with two of them, it's not really going to matter what the function is. It's going to matter what the region looks like, depending on whether I can do it in terms of y first or x first. Okay? So once I have my order of integration, then I want to find the limits for the innermost region. And basically how I'm going to do that is I'm going to start by looking at my region, and I'm going to use both methods and figure out which one actually works nicely. I'm going to take, if I want to try and do y first, I want to pick any vertical line, meaning looking at the entire region and picking a vertical line, and figure out where it starts and stops. If my starting or my stopping point is the same curve in both cases, I'm probably not going to want to do y first. Or if there's not clearly one starting function all the way through or one ending function all the way through, again, I'm probably not going to want to do y first. I can do the same thing with the x's by looking at any horizontal line and see where it starts and stops. And for these, I've drawn these little arrows here because I do actually mean when I say start, I'm going from bottom to top, so going in a positive vertical direction. Likewise, for the horizontals, I'm going in a positive horizontal direction, so going from left to right. Once I find the innermost limits, then I want to look at the outermost limits. And I'm going to do the same thing, essentially. The difference is I'm not just going to pick a line and look anywhere. What I'm then going to do is I'm going to take, now that I figured out where my first limits are, I'm going to squish my region to the other axis and figure out where the final limits are going to be. And so what I mean by that is if I'm doing x first here, then in this case I'm going to do y second. And so I'm going to squish my region over to the y-axis, not literally, but kind of pictorially in my mind. I'm going to squish it over to the y-axis and figure out where it first hits and where it ends on that y-axis. Same thing, if I start with y for my inner limits, then my x is going to be my outer limit. And in that case, then I'm going to squish everything down to the x-axis and figure out where the imprint is going to be. Okay? And so here I have some different regions, and we're going to look at kind of just setting up a integral, a multiple integral for these in terms of area. Again, for many of these, there's going to be more than one way I can do this, meaning I can do it dy dx or dx dy, but I just want to get the feel for setting these up in one direction. Okay? So for this first region, we're basically looking at a rectangular region. And so the first thing to think about for these is, as we did those last examples where we're actually evaluating, this is the only region you are ever going to have that has constant limits in both the inner and the outer integral. if I'm looking at constant limits anywhere else